Pythagoras' theorem. In order to understand what follows, you'll need to understand lines, angles, triangles, and squaring and squares. So
You'll be able to take a bath. Isn't there something about Pythagoras and a bath?
No, that was
Archimedes.
That was Archimedes. That was Archimedes.
So wrong Greek person.
Archimedes, but
we're sort of in the same era.
Ancient Greek.
Yeah.
Yeah. In statistics, there's an awful lot of squaring things and then adding them together, and this is where it all started from. Pythagoras' theorem. So if you were a builder in Egypt thousands of years ago, you could have travelled very light. If you wanted to measure a vertical line, all you needed to use was a plumb line, which is still in use. It's a weight on the end of a line, and that tells you what something's vertical. If you wanted to measure something horizontal, you just fill a trough with water or dig a trough on the ground and fill it with water. That'll tell you what was level. But if you wanted to do a right angle on the ground, you could use a loop of rope.
Okay.
And
didn't know that.
Yeah, the way you did that was you tied knots evenly spaced in the rope, say in this case 12 knots in the rope, and stretch it out so that there's 3 on one side, 4 on one side, and 5 on the other side. That gives you an exact right angle.
Oh yeah, it does, doesn't it?
And in fact, that's people are still using that. Some tilers sometimes use that to make sure that if they don't trust if the walls of the house are square, they can use that to make sure they've got
with the rope and the knot thing.
Just with the rope and the knots. And the thing about those three numbers is if you take 3 and square it, or the ancients used to do, just put a square of 3's on it, and if you take 4 and square it, then the long side is exactly the same area as those two put together. So the way Pythagoras' theorem is sometimes expressed is the square on the hypotenuse being the long side, right? The idea here is hypo under tenuse, like tense, it's stretched, so it's stretched under the right angle is the idea. But so the square on the hypotenuse is equal to the sum of the squares on the other two sides. So you put a square there and a square there, any size square, that side's going to be the same. For instance, with our 3, 4 and 5 row. Sorry?
That's really good. I'm just, again, the use of these visuals I'm finding really helpful, because to me what's just an abstract statement of the square and the hypotenuse, by actually seeing the square, it makes so much sense.
So 3 squared is 9, 4 squared is 16, 5 squared is 25, and 3 plus 9 is 25.
Yeah.
And as I mentioned, the idea of squaring numbers and adding them comes up in a lot of statistics, and this is where it started. So if we call now, but question is, how do we prove that's true? Actually, the ancients had a lot of ways of proving it, but here's a simple way. If we call the hypotenuse the hypotenuse.
That's a good name.
I thought so. The short side short and the middle length side middle, and we make 4 copies of it.
Yeah.
And then we rearrange them like that into a bigger square.
Yeah.
Then the square on the hypotenuse is that green area in the middle. And what that area is made up of, we put a board around the outside, and if we don't we don't go outside that square and we don't overlap any of those white triangles, and they all stay in there, then whatever the area is on the inside can't change. Might look a different shape, but if we move a triangle, the area is still going to be the same, because the area of the white triangle is going to be the same, and the area of the yellow square is going to be the same, so the green area is going to make up the difference.
Gotcha.
So if we just rearrange them like that, what we've got is, in the bottom left-hand corner, a square made of the short side. On the top right-hand corner, a square made of the middle side, and that's exactly the same area as the square on the hypotenuse.
Right. Okay. So hence I've heard the phrase square on the hypotenuse, and now I know what it actually is and looks like.
That's what it means, and that's Pythagoras' theorem in a nutshell. Thank you for watching.